Hello everyone, welcome to our discussion of section 2.3 where we will be talking about additional ways of finding the derivative of functions. Now so far, especially in section 2.2, we discussed using the definition of a derivative to find the derivative of functions. But as I'm sure you noticed, that's a long, protracted way of finding the derivative of functions, even though the nice thing about it is that it gets at the root and fundamentals of what it means to find a derivative. But in this section and the following sections, we will be discovering or exploring different techniques that are much quicker and much easier to apply in order to find the derivative of various types of functions. So of course our task is just make a little bit of effort to remember these different techniques. Okay, so let's begin. So firstly, we want to talk about how to find the derivative of a constant. And the derivative of a constant value that is always 0. In other words, we can say that dx of a constant value is always equal to 0. And this should be easy to understand because if you have y equals, or the function value equals a constant, right? So f of x equals, let's say, 5. Now that's a horizontal line, and we already know that the slope of a horizontal line is always 0. So this rule or this technique actually confirms what we already knew graphically. So the derivative of the independent variable, most usually we call it x, right? So derivative of x is always equal to the coefficient of x. In this case, 1, right? The coefficient of x in this case is 1. So derivative of x is 1 because the coefficient of x is 1. So we can write that d derivative of that with respect to x is equal to 1. Okay, and then thirdly, when n is some positive integer, then when we have to take the derivative of a function, of a power function like that, you've seen this a lot in polynomials, right? Terms like this. If we have to take the derivative of a term that looks like that, a single or a series of power functions like this, then we simply bring this power down and in front like that, and then we reduce that power by 1. So n comes in front and then times x to n minus 1 power. Okay, so we reduce that power by 1 as we do this. These are easy rules to remember, right? I hope that's what you think of these. So if c so here we had coefficient of x was 1, and the derivative of x was 1. Now, what if that coefficient is something else, such as a constant, any other constant like c? It could be negative, it could be a fraction, it could be a square root, it could be other roots, other kinds of numbers. So this c represents some kind of a constant. So if c is a constant, and f is a differentiable function. We talked about differentiability in section 2.2, right? So if an f is a differentiable function, then we can do this, which is tantamount to the same thing as that, but in this case, constant can be anything other than 1. So if we're taking the derivative of some constant that is multiplied by some function, then you can bring the constant out and in front and take the derivative of the function with respect to the independent variable, like that. So if you have a function multiplied by something, you can do that. You can bring the constant out and in front. Okay? Only if you have this situation, a function being multiplied by a constant, you can do that. Now, an item and technique number 5. So if we have two functions, say f, and let's call them function f and g. Are both differentiable, then if you have dx of f of x, two functions that are being added like this, then you can take the derivative. The derivative of the sum of two functions is equal to the sum of the individual derivatives. In other words, d dx of f of x plus d dx of g of x. Okay, so again, the derivative of the sum of two functions is equal to the sum of the individual derivatives. Okay, let's do the same. Number 6 is the same thing, but it applies to the difference between two functions. So if f and g then we have this situation. So d dx of f of x minus gx is equal to d dx of derivative of f of x minus the derivative of g of x. Of course, we talked about these notations in the previous section, 2.2. Okay. So far, everything should make sense, right? So item 7, if we have a trigonometric function like sine of x, the derivative of sine of x is cosine of x. Very easy to remember. And here's a little bit of a twist when we take the derivative of the cosine function. The derivative of the cosine function is equal to minus sine of x. Okay, so let's just apply what we've learned or what we looked at so far, these techniques, to different examples. Examples always help, don't they? So here we want to differentiate the following functions. So what if we have a function that is f of x equals pi squared? So what do you think? So what would be the derivative of this function? That's a constant, right? Pi squared is some constant value, 3.14 roughly squared, right? So the derivative of a constant is equal to 0, always. It doesn't matter what the value of the constant is. The derivative of a constant is 0. So f prime of x equals 0. Suppose we have a function like this, f of x equals 3/4 x to the 8th power. So now would be a good time to pause the video, answer this question on your own, and then unpause the video and compare your answer with mine. But before you pause the video, I will remind you that here we're making use of two of these techniques that we just looked at. One is this one, number 3. The power is brought in front, and then the power is reduced by 1 when we take the derivative, of course. And also this one, number 3 and 4. If you have a constant multiplied by a function, you can bring the constant out and place it in front. Okay, so those two. Use 3 and 4 to answer that question. Okay, so I'm assuming you've done that, and now you're back to compare my solution with your own, which is great. So this is the constant that is being multiplied by the function x to the 8th power. So we can, in the derivative of this function, or f prime of x, we can put this constant in front, multiply it by the power, by the positive power, or whatever power. And then what happens to this power? What happens to that power? It is reduced by 1. Right? Great. So let's simplify this. So we know that 4 is a factor of 8. So 4 and 4 factor of 8 cancel out. We get 2 times 3, or 6, right, after simplification. And then, of course, times x to 7th power. Now, isn't this quick when you compare it with what we did in section 2.2 when we applied the definition of a derivative to find a derivative? Isn't this much quicker and easier? So it's worth memorizing, isn't it? Okay, so another example. Suppose if we have y equals sine of t plus pi cosine of t, right? Now, how easy is that to find the derivative for given these techniques that we just introduced? We know that the derivative of the sine function is simply the cosine function. So let's write it down. So y prime, this is simply cosine of t, plus, I got to be careful here with cosine of t. The technique is the derivative of cosine is minus sine of x, right? So here we have plus minus 1 pi, which is the constant, times sine of t. So in other words, we have cosine of t minus pi sine of t. Look at how easy that was when you compare to the laborious work we had to do with the definition of a derivative to find the derivative of a function. So again, all these techniques are worth memorizing. Look how easy they make our job when we try to find the derivative of a function. Okay, so in the next example, suppose if we have d, and if we have b as a function of y, variable y, function b as a function of variable y is equal to cy to minus 6 power. So then, again, please pause the video, complete the solution on your own, and then come back to the video. I hope that you're doing that. Okay, so the derivative of this would be b prime y equals, this c is already in front, let's bring the minus 6 down, times c, y, and then minus 6, we have to reduce this by 1, right? So let's simplify this. B prime y is equal to minus 6c times y to minus 7 power. Of course, in math, we work so hard in Math 124 and Math 126 to emphasize that we want to convert these negative powers to positive ones. So let's do that. So b prime y is equal to minus 6c divided by y to positive 7 power. Like that. Okay. So let's do another example. Example E. Suppose we have y equals x to 5/3 power minus x to 2/3 power. Okay, please go ahead, pause the video, finish this on your own, and then come back. All right, I assume you did that. So this power comes in front, and it is reduced also by 1, right? So 5/3 minus 1. Then we have a minus here, so minus here. The 2/3 is brought down and in front, times the x variable, and then the 2/3 is reduced by 1. So y prime is equal to 5/3 times x. Let's take the common denominator there, and we have 5 minus 3, it would be 2/3. And then minus 2/3, right? Again, the same thing. Take the common denominator there. We have 3 and minus 1/3. So minus 1/3. Okay. Okay, so, I mean, these are, especially this one, we want to convert to a positive power. But as you recall from basic algebra, any rational exponent can be written in terms of a radical expression, right? So let's do that. This is one way of concluding it. We can conclude here, but I would prefer not, especially because we have a negative power. So we say or, and then y prime equals, so we have 5/3. This is the, so we have third root of x squared minus, and we have here we have a negative power. We want to write that in terms of positive, so we say minus 2/3 times square root of, the third root of, this denominator is the root, is the index of a root, and so we have third root of x. Okay, this goes back to the properties of radical expressions. Okay, you want to, if you have trouble following this, please review that, or come by my office, or join a WebEx session for me to explain that for you. Okay, I'll be happy to do that. But all I did was convert these exponents, rational exponents, to radical expressions. Okay, so we can do that as well. Okay, so let's do more of these. So we have a function y equals square root of x times x minus 1. So let's convert this to a rational exponent because it's easier to distribute it that way. So we have x to 1/2 power times x minus 1. Then let's distribute. We know that from the properties of exponents, we know that when the base is the same, we can add the powers. So we have y equals x to 1/2 power times x minus, of course, x to 1/2 power. And let me move this up a little bit. So the power of this x is 1. The power of this one is 1/2. 1 plus 1/2 is 3/2. So we have x to 3/2 power minus x to 1/2 power. Let's see. Okay, so now that we've distributed this, now we can take the derivative easier. So this basically, this transition to this, and now let's find the derivative. So we have y prime, this constant comes in front, this power I should say, 3/2 times x, and then the power is reduced by 1. Same thing here. Like that. So here we have 3/2 minus 1, which would give us 1/2. And minus 1/2 times x to 1/2 minus 1 would be minus 1/2, right? Minus 1/2. So let's rewrite this in terms of a radical expression. So we have y prime equals 3/3 square root of x, because this 2 in the denominator is the index, right? Index of this root function. And then we need to rewrite this so the power is positive. So it will be minus 1 over this 2, which is already in the denominator, times square root of x. Like that. Okay, so we have the full derivative of that original function. So let's do another example. This would be G, example G, and we have y equals square root of x plus x divided by x squared. So first let's split this into two fractions and combine the x variables. So y is equal to square root of x over x squared plus x over x squared, right? So let's simplify this a little bit. So we haven't taken the derivative yet. Again, I'm hoping you're pausing the video as we're doing this, as you're watching this, and writing down your own solution before you unpause the video and compare your solution with this. So we have x here, which is square root of x, which translates into x to 1/2 power divided by x squared, plus, of course, that x, which has a power 1, minus 2, right? From basic algebra, we remember the rules that govern the exponents. So when the bases are the same, we can subtract the power that's in the denominator from the power that's in the numerator when the bases are the same. And that's what I did. I subtracted this from this power, which is 1. Okay, so we need to actually do the same thing here. So y equals x 1/2 minus 2 plus x2 minus 1 power. And this, of course, this is 1/2 minus 2, so this is minus 3/2. So y equals minus 3, x2 minus 3/2 power plus x2 minus 1 power. Okay? So this is not, of course, the way we're going to leave our answer. I mean, we just did this. We transformed everything here that was in this neat form with no negative powers. We transformed this into this. Why? Because it's when the function is written in this way, it's easier to apply these techniques that we just learned. Okay, that's why. So then y prime would be just bring this power in front, so minus 3/2 times x, and reduce this power by 1. So minus 3/2 minus 1. Then we have a plus. Then bring this negative 1 in front, multiply it by x, and reduce that power by 1, like that. Okay? This is just following that rule that we introduced. This one. We're just applying this rule, number 3. Okay? So let's simplify this. And of course, at the end, we do not want to leave things with a negative power. So we have minus 3/2 times x. This is minus 1.5 minus 1. That's minus 2.5, which is minus 5/2. Plus times minus 1, that would be minus x to minus 2 power. Okay, so now that we have the derivative, we want to convert it so these negative powers don't exist anymore. So let's do that. Y prime is equal to minus 3 over 2, this 2, times, notice this denominator represents the index of this root function, and the minus 5 represents the power of x inside the radical, but when we bring it to the denominator, it becomes positive. So it's no longer going to be negative 5 over 2. It's going to be positive 5 over 2. So it's going to be square root of x to the 5 power. And of course, we can simplify this, and we will. So minus, this is easy to transform, right? That 1 over x squared. Okay. Let's see. So we have, so that is plus times that. I'm just double checking these things just to make sure. Minus 2. Let's see. 1 minus 2. Yes, so that should be correct. And then we have minus and minus here and that. Okay, so now this is fine, but this one is not, because we can simplify this. The index is, of course, 2 for a square root, but this is x to the 5th power. So let's see. So y prime is equal to minus 3 over 2 times square root of, we say, x squared squared times x, right? That we can rewrite x to the 5th power like this, x squared squared times x. So that would be x to the 4th times this, it would be x to the 5 again, to the 5th power, minus 1 over x squared, and then of course y prime is, now we have a term on the inside of the square root that is in the, to the 2nd power, so we can remove this from inside and put it outside. So we have minus 3 divided by 2 times x squared. So this x squared loses this outside power as it leaves the radical expression. And then, of course, we are left with just square root of x. Okay, minus, let's not forget, minus 3 over 2 times x squared, square root of x, minus 1 over x squared. Okay, and we leave it like that. Okay, so let's continue with more examples here. That was g, so this will be h. We want to find the derivative of y equals sine of theta over 2 plus c divided by theta. All right? Okay. So let's rewrite this so it's easier to take the derivative of. So we have y equals 1/2 sine theta. Of course, we're going to take the derivative of this with respect to theta, right? Theta is the variable there. Plus c times theta to minus 1 power. Okay, theta is our variable there. Okay, so we learned that the derivative of the sine function is the, do you remember what it was? Let me bring it back. If I can find it. There it is. The derivative of the sine function is cosine function, and cosine function is minus sine function. So we have 1/2 cosine of theta, right? We're done with, this should be y prime. And then we have a negative power here. So plus that negative power comes in front, multiplies itself by the constant c, and then we reduce that power by 1. So -1 -1. Okay, so we have y prime equals 1/2 cosine of theta plus times minus is minus c theta to -2 power. Of course, we need to rewrite this in terms of a positive exponent. So let's do that. Theta squared. Okay, so now we can leave the answer like that. Okay, so let's change the types of examples a little bit, but these examples are more interesting because so far every example that we did was just making use of the techniques we introduced in this section. But in the upcoming examples, we're going to have to remember the things we've learned in the previous sections, so they are more involved in that way. Okay, so suppose we want to find, actually let me put this on the next page because I don't think I have enough room on this page. So let me go to a new page. I don't want to split the solution into 2 pages if I can help it. That'll be that way when you print these lecture notes, if you want to, then the whole solution will be on 1 page. Okay, so we have this, find equations of the tangent line and normal line. I don't know if you know what a normal line is from other classes because we haven't talked about that yet. It's another way of calling 2 lines that are perpendicular at to each other. So a normal line would be, a tangent line is obvious, and then a normal line would be a line that is perpendicular to another line. Okay, so i.e. the perpendicular line. Okay, so we want to find equations of the tangent line and the normal line or the perpendicular line to the curve, to the given curve, at the given point. Okay, so here's the curve that we have. We have x squared minus x to the 4th, and the point is 1, 0. Well, we've already learned that the tangent line, if we know a slope of any line and a point on that line, we can write its equation. So we know that if we take the derivative of this function, this curve, and evaluate it at this x value, we're going to be able to find the slope of the tangent line. Okay, and then we have one point. We have a point on the line, on the tangent line, and we can find the slope using the derivative. We combine the slope and this point, we can easily find the equation of the tangent line. And we, of course, know how to find the perpendicular lines because 2 lines are perpendicular when the product of their slopes is equal to -1. Okay, this is something we learned in college algebra or Math 124 and also Pre-Calculus 1, Math 126. If you happen to have taken other math classes like the finite math, you would have seen this also there in that course. Okay, so the tangent line first, let's find that. And so we have, let's take the derivative of this. Y prime is equal to 2x, right? Minus 4x cubed. So let's replace x with 1. So y prime is equal to 2 times 1 minus 4 times 1 cubed. And so y prime, so this will be 2 minus 4, or y prime is equal to minus 2. So this is the slope of the derivative at 1, 0 is the slope of the tangent line. And so we know the slope of the tangent line, we know a point on the tangent line. So recall from basic algebra that we had the point slope form of a linear equation. Right? Remember, we have that equation, so let's apply it. In this case, y is just y, minus y1 is 0. M, we just found that's the slope of the tangent line. X is just x, minus x1 is 1. So we have y equals, let's distribute the negative 2 into this parentheses. So we have minus 2x plus 2 as the equation of the tangent line. Okay, let's find the normal line or the perpendicular line to this. i.e. perpendicular line. Okay, so once again, so recall, let's recall this, recall that for two lines to be perpendicular or normal to each other, their slopes must satisfy this condition that m1 times m2, or the slope of one line times the slope of the other one, must be equal to -1. Okay, so we already know the slope of m1 in this case is it was -2, right? We found it up here. That's the slope of the tangent line. So we're going to find m2, which is the slope of the perpendicular line. So m2, from this simple equation, m2 would be 1/2. Okay, so now we know the slope. We know that the perpendicular line also goes through this point 1, 0. So once again, we can apply this helpful equation or formula to find the equation of the perpendicular line. Let's do that. So y minus y1 equals m times x minus x1. Y minus 0 equals 1/2 times x minus 1. And then we have y equals 1/2 x minus 1/2, right? After distributing the 1/2 into that. So this is the I should have said actually equation of the, so this is the equation of the tangent line. Of the tangent line. And this one would be the equation of the normal line. Like that. Okay, so you see what I mean when I say these examples are more interesting, because they force us to use the stuff we've learned before, which is good. It's always good to do that. All right. It'll improve our skills and memory that way. So, I keep forgetting to remind you to please pause the video when I go through each example, but I hope this has become an automatic habit for you, and that once I write down an example, please don't wait for me to remind you. Probably you'll be annoyed if I kept reminding you. Just pause the video and write down your own solution before you watch my solution. Because I really want you to do well in this course, and that's the way to do it. You just don't want to copy my thinking down. My thinking is really worthless to you. The valuable thing here is your own solution, which if incorrect, in case they are incorrect, then you can correct by comparing with my solutions. But without that comparative or comparison with your own solution, my solutions become worthless, okay? Because copying them down isn't going to help you understand this material. Okay, here we go over more examples. We want to find the first and second derivative of the given functions. Okay, so here we have function g of r equals square root of r plus third root of r. Okay. So the first and second derivative would be, so g, since this is g of r, we're going to call that g prime of r and g double prime of r. But before that, let's rewrite these in terms of rational exponents, because we know that doing that will help us find the derivatives easier. So g of r is equal to r to 1/2 power plus r to 1/3 power. Okay, now g prime, or the first derivative, g prime of r, or the first derivative, is simply bring that power down and in front, times r, reduce that power by 1, plus bring the 1/3 in front, multiply by r, and reduce that power by 1. Okay, let's simplify. So g prime of r is equal to 1/2 r to minus 1/2 and plus 1/3 times r, 1/3 minus 1, that would be minus 2/3, right? So minus 2/3. Okay, so definitely we don't want to leave these powers as negative, but I'm going to leave a little bit of a blank space here, and then I'm going to jump to the second derivative, because before I do that, well, we can do that later too. We can do that, let's do that later. So let's simplify this. So we have g prime of r would be 1/2, that's this 2, And then let's write this in terms of a positive power and radical form. So it'll be square root of r. Okay, because that 2 is the index here of this root function. And plus, of course, 1/3, and we want to write this in terms of a positive power, and the index this time is 3, so it's a third root of r to the second power. So 1/3 times third root of r squared. Okay, so that's g prime r, or the first derivative, right? But now let's use this to obtain the second derivative, okay? Because this would be, we'd have to rewrite this in that term. So the second derivative would be g double prime of r is equal to, now bring this power down and multiply it by this constant that we have in front. So minus, I'll do this step by step. So minus 1/2 in front times 1/2, this one, times r, to reduce this power by 1. So minus 1/2 minus 1. Then we have plus, we have a 1/3 there, times, let's see. So I want to do the same thing I did here. So let me put 1/3 in this parenthesis and just write minus 2/3. So minus 2/3, that would be that power, bring that in front, minus 2/3 times 1/3 times r, and reduce that power by 1, like that. Okay? All right, so let's simplify this. So g double prime r is minus 1/4, right? Minus 1/4 times r, minus 1/2, minus 1, that's minus 3/2. And let's see, so minus 3/2, and then how about here? Minus 2 times 1 is minus 2/9, minus 2/9, and of course this would be times r, minus 2/3 minus 1. So we take the common denominator and we get minus 5/3, right? Like that. Okay, of course we don't want to leave this. This is the second derivative, but we don't want to leave it with negative power. So let's simplify this. G double prime r is equal to minus 1/4. The index is 2, so we have a square root here. Square root of r to third power. Okay, and this is of course now positive because we moved r to negative 3/2 power down to the denominator. Okay, so if you rewrote this, it would be r to positive 3/2 power, not negative 3/2 power. Okay, and of course we're able to simplify this, and we will. So minus 2/9. This is the third root of r to the 5th. Third root of r to the 5th. And of course, we can simplify this as well. Okay, so to do that, we do g double prime of r is equal to minus 1/4. This we can write as r squared times r, right? That one. Minus 2/9, third root of, this is the third, so we can write this as r cubed times r squared, right? That still would be r cubed times r squared would be r to the 5th. So now we have a square root and a term that is the second power on the inside being multiplied by another term. We can move this term outside of the radical and put it in front. So g double prime r would be minus 1 over 4. In the process, this power is dropped or canceled. 4 times r, square root of r, minus 2 over 9, third root. We have a term that has an equal power to the index, a power equal to the index of the root function. And so this one can come out because it's being multiplied by the other term. It can come out. If this was plus or minus, we could not do that, right? You know that. So this is being multiplied, though, so we can bring this out. In the process, it'll lose the power, so it becomes r, 9r, third root of r squared. And we stop there. So, so let me extend this so that is an index to the root function. Okay, that 3 is not a power of the r on the outside. It's the index of this root function. I wrote these too close to each other. Sorry about that. But that 3 is the index of this root function. All right, so then we can declare this as our final answer for this. And this is the second derivative. Okay, like that. Okay, so let's do, what did we do? We did all these numerical problems. So let's do a word problem. So if a tank holds 5,000 gallons of water, so here is, gives the volume of the water remaining. This is the V represents the volume of water remaining, not the one that has been drained, as a function of time. So 5,000 times 1 minus 1 over 40 t squared. And we are told that t varies between 0 and 40. So this would be in minutes, 40 minutes, between 0 to 40 minutes. So we want to, given this information, tank after, so the rate at which water is draining from the tank after A, 50 minutes, or 5 minutes, sorry. A, 5 minutes. B, 10 minutes. And C, 20 minutes. Okay, so just thinking about this conceptually, we would expect that this one to be a higher rate than the other ones, because at this point there is the water drains from the bottom of the tank, and at the beginning of this drainage there is more water in the tank, so it has a higher pressure exerting on the water exiting the tank. So we would expect this value, this rate at 5 minutes, after 5 minutes to be higher than after 20 minutes, because most of, or if not most, at least half of the water has left the tank at that point, and there's less pressure on the remaining water to leave the tank. This is just conceptually thinking about this. So, and D, and so I think so that would be that 20 minutes, and then at what time. So, and also they want us to write down at what time. So first we want to do that. Then they're asking us, I guess this would be part A and this would be part B. So at what time is the water flowing out the fastest? And of course they ask the slowest. Okay? All right. So if the water that is remaining in the tank at any given time over this interval from 0 to 40 minutes is given by this function, volume of the water is still remaining in the tank at any time over this interval given by this function, then the rate at which that the water is leaving, or the change in the volume given time, would be the derivative of this, right? The change in volume according to time would be the derivative of this function with respect to time. So let's first find the derivative of this function. To do that, what I would do, I would first expand this binomial to second power, expand it. Okay, you can FOIL it, or you can use the shortcut formula that we learned about in basic algebra. Either way is fine. Oops. So let me before that, so I want to expand that. Okay. So we have that. And then let's distribute this 5,000 into that. minus 1 over 20 times 5,000 minus 250 t. Please double check these numbers. And 5,000 times 1 over 1,600. So plus, let me use my calculator to see that. So we have 5,000 times 1 over 1,600. 1 over 1,600 times 5,000. Okay, it's 3.125. So let's use that number without any rounding. So we have plus 3.125 t squared times t squared. Okay, so now if this is our function for the volume remaining in the tank, volume of the water remaining in the tank, we can easily take the derivative of this. So that would be v prime. The derivative of a constant is 0. The derivative of this is just minus 250. And of course we know that this would be plus 2 times 3.125 times t. Reduce this by 1 is just t. Okay. So what do we get? We get v prime. We can put this first. So this would be, or we can keep it the way it is. So 2 minus 250 plus 6.25 t. Right? So 2 times 3.125, 6.25. Okay. So this is the derivative of that, which tells us the rate at which water is draining from the tank. So this is the derivative function. Moment. And we should say that that's what we're talking about at any given moment in this interval. But they want us to calculate that rate for 5 minutes after draining has started, 10 minutes after it has started, and 20 minutes after the drainage has started. So let's do that. So that would be the next set of calculations. So after 5 minutes, we have v prime equaling minus 250 plus 6.25 t, and of course this would be 5. This t would be 5, so v prime minus 250 plus 6.25 times 5, and the units of time is in minutes. And so what do we get? We get, let's bring this calculator again. So we have 5 times 6.25 minus 250. So we have minus 218.75, right? So minus 218.75. Of course, the units would be gallons. per minute, right? I'm sure you noticed that the rate is negative because it's the volume that, remember that the original function for this was measuring how much water is remaining in the tank, right? So this being negative means that that much gallons per minute is flowing out of the tank. The volume is dropping by this rate, 218.75 gallons per minute after 5 minutes of drainage. So this is the volume that has left the tank. So it's negative. Okay, so after 10 minutes, after 20 minutes, okay, so this was a word problem that we did using the derivative. There will be more examples like this coming up during our in-classroom activities and also during your discussion sessions with your discussion session instructor. So I'm sure you noticed that I kind of did these last two pretty quickly. The reason is at the time I'm recording this video, it's pretty windy outside, and for some reason, and I don't know the reason for this yet, when the outside of this classroom where I'm recording this is windy, and this has happened before, the microphone that I'm wearing picks up that wind occasionally on that sound is picked up by the microphone that I'm wearing. So in order to wrap up this session, and we were at the last part of this anyway, this was the last example, but I wanted to stop recording before the sound of the wind that is picked up by the microphone gets any worse. Okay, so I want to thank you for watching this video until the end. And I trust that you'll let me know if you have any questions. So for now, have a nice day, and I'll see you again next time.